Today we'll be looking at polynomial functions. Our objectives will be to identify polynomial functions and equations, to determine the leading coefficient of a polynomial function, to determine the degree of a polynomial function, to identify turning points of graphs of polynomial functions, and to predict end behavior of polynomial functions. So let's begin with a definition of polynomial functions and equations. A polynomial function is one that can be written in the form a sub n times x to the nth power plus all the way down to a sub 2 times x squared plus a sub 1 times x plus a sub 0. We've actually already been using polynomial functions this semester. We just didn't call them that. Let me show you a couple of those. The first function I have here for you is 3x plus 6. You would know that as a linear function. Well, it turns out it is also a polynomial function. It just uses this much of that definition. The next one you have here, you already recognize as well. It's a quadratic. You know it because it's 2x squared plus 4x minus 7. You also know that its graph would be that of a parabola. And it only uses that much of this definition. The others down here use more than that, and so they're the ones we haven't looked at so far, but they are polynomial functions. Now let's look at leading coefficients of polynomial functions. The leading coefficient is just the coefficient of the term with the largest exponent. So let's look at those same four functions and pick out the leading coefficient. In this one, it is a 3. In this one, it is a 2. In this one, it's a 7. And in this one, it's a negative 6. I do, however, want to ask you what would happen if you encountered one that looked like this. First of all, you would want to write it in descending order, which would give you negative 4x to the third power plus 3x squared plus 6. Then it's legal for you to tell me that this right here is your leading coefficient. Let's move on now to degrees of polynomials. The degree of the polynomial is the largest exponent. Let's once again take these same four functions and I'll ask you for their degree. Well, you don't see an exponent written here, but just let me remind you that's a 1. So the degree of this first function is a 1. You would tell me it's a first degree polynomial. This one has a degree of 2. It is a second degree. Here it's a fourth degree, and here a fifth degree polynomial. Once again, if you will write it in descending order, that leading coefficient and the degree will jump right out at you. Let's now look at turning points. Turning points occur when a graph changes from increasing to decreasing or from decreasing to increasing. We'll look at our same four functions and let's talk about them one at a time. Let's look at the first one, and what we have, remember, is a linear function. Let me ask you, is there ever a place where this linear function turns and goes back downhill? Well, the answer is no, there's not. So if that doesn't happen, then this function has no turning points. Let's continue on and look at the next one. This time I have a parabola, and that got chopped off right here. I'm just going to close it in there so you see it. This time, do we have a turning point? It's the place where it changes from decreasing to increasing or increasing to decreasing. Well, your function is decreasing, 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 all the way down to right here, and right there is your turning point, and then it starts going back up. Now, in parabolas, it turns out that that turning point has a special name, and we've already talked about that. What is it called? You would know it as a vertex or as a minimum, and that's exactly what it is. The more generic term for it is a turning point. Let's look now at our third function. Its graph looks like this. It's a degree 4, and it has some turning points here. It's decreasing down to right here. There's a turning point. Then it starts going uphill, and it goes up until right there. and then there's another turning point, and it goes down to right here, and then there's another turning point, and it goes back up. So in this one you would see 3 turning points. And then let's look at the last one. It's a 5th degree polynomial, and so let's look at what we see here. On the screen right now we see it decreasing down to right here, and then it increases up to right here, and then it starts down again. So we only see 2 turning points on the screen right now for that one. You can remember turning points because they're just like maximums or minimums on your function. And as a matter of fact, some textbooks will actually call them local maximums and local minimums. Let's continue now with end behavior of polynomials. And let's start with our same 4 functions. When I talk about end behavior, I'm talking about what happens on the graph when you get to each end of the graph. I'm looking at when x gets really large, going toward positive infinity, what happens to f of x. Remember that f of x, you're going to think of it as a y. And I'm also asking what happens when x gets really small, moving to the left, and I want to know what happens to y then as well. So let's look at our first graph. Once again, we have the line. Now this one's not too exciting because the end for it simply continues on, and it is rising. And these are the 2 terms that we're going to use for end behavior. We're going to talk about rising and falling. So this one is rising, and this end is doing what? It's going down, so it is falling. On the line, that's not a very big deal, but let's continue on. Back to our parabola, and let me close it in again. I'm still looking at end behavior, so I want to know what happens to the outside edges of the graph. Well, on this side over here, this is going up, so it is rising. And on this side, what is it doing? It is also going up, so it is also rising. So on this graph, both ends are rising. Now let's look at our 4th degree polynomial. Once again, what's happening on this end of the graph? It's rising. And what about this side? Also rising. If it's going up, it's rising. And then let's look at our very last one. And let's talk about the end behavior here. On this end, it's going up, so that one is rising. And over here, what is happening on this side? It is falling. What we're going to do now is we're going to look at some rules so that you can predict the number of x-intercepts, the number of turning points, and the end behavior of polynomials without ever seeing their graphs. So let's begin with those x-intercepts and turning points. By definition, a degree n polynomial, where n is greater than or equal to 1, has at most n x-intercepts and at most n minus 1 turning points. Now, this part right here is simply telling you that we at least have a line. It's not just going to be y is equal to a number. So we do at least have a linear equation there. And what that tells me is that if I have a degree 1, meaning a linear equation, I have at most 1 x-intercept and at most 0 turning points. Well, remember a minute ago when we graphed that line? That's exactly what happened. So let's look now at the rest of those polynomials and see how these rules apply to them. The first one is a 2nd degree polynomial. What this tells us is it can have at most 2 x-intercepts and at most 2 minus 1 or 1 turning point. Well, let's look and see if you see those. Let me close that back in. There are 2 x-intercepts. There's one of them. There's the other one. And at most 1 turning point. Right there it is. Now, without ever graphing that, you could have told me that much information. I also want to make sure that you understand the importance of that turning point. Sometimes we make the assumption that this graph is going to continue up through here in the direction it's moving. And on a parabola, that is true. But it's this rule right here that guarantees me that that graph can never come back up here and turn back down again. because then it would have a second turning point. And this part right here says it can have at most one, and I already see it right there. So I'm guaranteed that this graph will never turn back down again. Now on parabolas, that probably wasn't a big deal to you, but on some of these others in a minute, it's more important that you realize that. Let's look now at our next one. Here's our fourth degree polynomial. And what this tells us is that it can have at most 4 x-intercepts and at most 3 turning points. So let's look and see. I see 2 x-intercepts, there they are, right there, and I see 3 turning points, right here. Now let me ask you a question. Can there ever be a place where this comes back down and gives me another x-intercept? Think about that for just a second. I know it's legal for me to have another x-intercept because it says I can have at most 4. But it also says I can have at most 3 turning points, and I already see all 3 of them right here. So I'm guaranteed that this graph can never turn and come back down. So this part of it over here could never happen. That also holds true for this side. And so what that means in this graph is that these 2 intercepts that I have right here are the only ones I'm ever going to have. And then let's look at our last one. It has a degree of 5, so it can have at most 5 x-intercepts, and it can have at most 4 turning points. Look at this and tell me, how many x-intercepts do we see? 1 right there. And how many turning points do we see? 1 right here and 1 right here. Now here's what I need you to understand. This stuff over here is telling me that it has at most 5 x-intercepts and at most 4 turning points. It doesn't mean it will have 5, and it doesn't mean it will have 4 turning points, but it can have at most that many. Now, I have no guarantee here by what you see on the screen that this graph doesn't come back out here and turn back up and do this right here. Nothing over here would stop that from happening. It would have another turning point if it did that, and it would have another x-intercept. But I'm allowed to have those based on this rule over here. As a matter of fact, it could go one step further. It could turn and come back again. Give me another turning point and another x-intercept. I would have 1, 2, 3, 4 turning points. That would be okay. And I would have 1, 2, 3 x-intercepts. Now here's what I want you to understand. I just don't know what's going to happen over on this part right here. I can make no prediction about it based on what you see on the screen or what you have written over here, because there's still room in here for these things to happen. If you see all of the x-intercepts or you see all of the turning points, either one, then you're guaranteed what happens with the rest of the function. Let's talk now a little bit more about end behavior. What we're going to do now is we're going to predict end behavior without ever drawing the graph. For a degree n polynomial, where n is greater than or equal to 1, it is at least a line. If n is even, then here's the things that can happen. If a is greater than 0, that's that leading coefficient, is greater than 0, then the graph rises both to the left and to the right. If a is less than 0, then the graph falls both to the left and to the right. Now, I know you're going to think, how in the world am I going to remember all of this? Well, tell me what you already know about a parabola. It's a degree 2, and if a is positive, it opens up. Well, it's rising to the left and it's rising to the right. That's your way of remembering this piece right here. The other thing you know about the parabola is that if a is less than 0, it opens down. That means your parabola falls to the left and falls to the right if a is less than 0. What you gain from this is that you also know that the end behavior of a 4th degree polynomial is the same. And you also know the end behavior of a 6th degree is the same. but that may help you remember what to do on these even degree polynomials. Now let's look at the odd degree. If n is odd, then when a is greater than or equal to 0, the graph falls to the left and rises to the right, meaning you get something that looks like this. If a is less than 0, the graph rises to the left and falls to the right, something that looks like that. I don't have any neat tricks to help you remember that one. You're just going to have to know that one. So let's look at some of our graphs and see if these things make sense. Let's go back to our same three polynomials we've been using. The first one is our parabola. It is a degree 2, and its leading coefficient is positive. Therefore, it rises both to the left and to the right. Well, we already know that. Here it is. Let's look at our next one. What about this one? A fourth degree. Well, once again, it's even. It would be a 4 right there. So its end behavior is going to behave the same as the parabola. Its leading coefficient is positive, so its end behavior will rise both to the left and to the right. And then our last one is a fifth degree polynomial, which means it has an odd degree, and its coefficient is negative. That means that by looking at that information right there without ever drawing its picture, I would predict that it rises to the left and falls to the right. Let's see if it does. Rises to the left and falls to the right. So these rules give you a picture of end behavior without even having the graph in front of you. That's all I have for you today for polynomial functions. Have a great rest of the day, and I'll see you again soon. Bye-bye.